Hello, this is Dr. Muhammad, and this is another video under the analysis of statically indeterminate structures. And still we are talking about the topic of the moment distribution method, and today we're going to talk about the frames without sidesway. So last time it was continuous beams. I think that we have spent two videos on continuous beams. Today we are going to talk about frames without sidesway, and in the next videos we're going to talk about frames with sidesway. Okay, so let's start with this and have an introduction to our frames without sidesway using moment distribution. First of all, we need to highlight that the procedure for the analysis of frames without sidesway is similar to that for the analysis of continuous beam. So you are not going to find a great deal of difference between the two. So if you are familiar with how to use moment distribution for continuous beams, you're going to find it is pretty easy for you to use it for frames without sidesway. The main difference between the application of moment distribution on continuous beams and frames without sidesway that we might face more than two members may be connected to a joint of a frame. Commonly, whenever that we have a continuous beam, we are facing the situation that at one particular support or joint we have two members only, to the right and to the left. So this is easy for us to tabulate whenever that we are using the tables, for example, to report the factors and the fixed end moments and the carryover moments and so on. However, in the frames, it might happen that we are facing a situation where that we have, for example, this is a frame that we might face. So as you can see here, this joint is having like three branches. So in this case we are going to find that it's a little bit not straightforward like the case of the continuous beam. We need to put this, or three branches, we need to put two of them, and then we are going to put the third one or the third branch outside of the table, as we are going to see, and then we can carry out the same steps. Okay, so it is only one thing, small tiny difference between the two. Okay, so more than two members can be connected to a joint of a frame. In such cases, care must be taken to record the computations in such a manner that mistakes are avoided, as we are going to see in our examples. Actually, some engineers like to record the moment distributions and fixed end moments and the carryover moments on the members themselves. Okay, so they like to record the moment distribution computations directly on a sketch of the frame. So they like to have the frame itself, and then they put the moment distribution and the fixed end moments and the carryovers on these branches of the frame elements itself, or the frame members itself. This is okay, and it is based on the practice of the engineer itself, but again it is based upon your preference, which type of procedure you like and representation method you like. If you like to do it, which is moment distribution computations directly on sketch of the frame, it is okay, or others, which is including our today's video, we're going to use a tabular format for such purposes, which is like, I think that it is more straightforward. Tabular form is going to make it easy and very straightforward for us. Okay, anyway, this is an introduction to what we are going to do for the frames without sidesway. And I think the best way is to have an example to show how we can implement the moment distribution method on frames without sidesway. Okay, let's go with this example and see how we can work with it. The example says determine the member end moments. So here the main thing that we want is the member end moments for the frame shown. This is the frame, by using the moment distribution method. Actually, this frame we have used it before when we were discussing other types and methods, but today we're going to apply the moment distribution method. So let's have a look on the geometry of this frame and the different properties given in this example. First of all, the first important thing is to look to the boundary conditions. So we have here at joint A, it is fixed, similar at joint B, it is fixed also, and at joint E, as you can see, it is hinged. The moments C and D, the joints C and D, they are the joints where that we can call them free to rotate, if you want to tell about this. So they are the points, or we can say that they are the two joints which are free to rotate. Actually, joint A, it is fixed, so it is not allowed to rotate. Joint B, it is fixed also, the same, it's not allowed to rotate. Joint E, it is allowed to rotate, and the moment here is 0. So actually no need to put it as a joint that we need to know the moment at, because remember that the final goal for us is to obtain the final or the member end moment. So at this member, which is DE, the end moment here is 0 because we have this hinge end. This means that the moment here is 0, so no need to do additional work for this. And for A and B, they are fixed, so no rotation. So here the rotation is 0, but we do not know the moment. However, at point C and D, the moment is going to be developed at these 2 points, and in the same time there is going to be some some kind of rotation for the element itself. Okay, so as you can see here, so the free to rotate, so there is rotational angle, and in the same time there is moment. But here at E, there is rotational angle, yes, but the moment is known, which is 0. Okay. If you look to the concentrated load, let's remove this. So if you're going to look to the concentrated loads here, or the external loads applied in the system, you're going to find 40K, which is concentrated loads applied at point AC, at member AC, at the middle, and we are having distributed load along members CD and DE. Okay, so we have these are the external loads that we have. Okay, another thing which is important, we are telling that this frame is, the frame is sidesway is prevented. So we want to be sure that it is prevented. Actually, if you go back 3 videos, I guess, I was discussing about this frame, and I was talking about why we call it frame without sidesway or sidesway prevented, and I mentioned about the inextensible members and the fixation and the contribution of each boundary condition. So I'm going to repeat it here quickly, just a reminder of what I've said before. So first of all, if you think about the points that is allowed to move, then, and what are the joints that are not allowed to move horizontally or translational, then point or joint A, joint B, joint E, they are not allowed to move. Okay, we have A and B, they are fixed. Point E, it is hinged, so it's not allowed. And we have point C and D, we do not know whether that they can be allowed to move or not. And we said that if you look at this level, which is the level at CDE, you're going to find that we have at the end a point or a joint that does not allow any translational movement. And point C, and point D, they are connected to this point with inextensible members, which are DE and DC. This means that, and we said before that the axial deformation of these members, they are going to be negligible. This means that C and D, they are not, or they are prevented from any translational movement. Why? What is the reason? Because we have, at the end, we have a point or a joint that is not allowed to move because of the existence of this hinge, and they are connected to this joint with member DE and DC, which are considered to be inextensible. This means that the entire frame is not allowed to move laterally. So this is a frame without sidesway. Okay, so now we are ready. We have known that what is the characteristic of this frame. One thing that is important that we want to say in the moment distribution, you're going to find that we concentrate on joint C and D, and we are going to bring the, or calculate the moment distribution factors at these 2 points only, and we are not going to make it for the others, because as we said, we want to balance these 2 points, and then we are going to find that the end moment here, it is going to be 0. The end moment here is going to be developed based on the carryovers coming from these 2 points. Okay, so we are going to discuss about this in the next slide. Okay, so now we have everything known now. Just I want to remind that we have AC inertia. It is 800 inch to the power 4, similar to BD. However, the girders, they are double of the columns. Okay, so here we have 800. The girders, they are 1600s. Okay, so that's important to highlight because it will contribute in the moment distribution factors. E is constant for all members, 29,000 KSI, and the distances are 30 foot and 30 foot, and here it is 20 foot for the column's height. Okay. Now let's go to the next slide. The first step, as we have done it many times before, is the distribution factor. We need to look to the distribution factor at 2 different points. Okay, so we have distribution factors at point C, okay, or at joint C, and we are going to have a distribution factor at joint D. Okay, so we are going to look to this joint and calculate the distribution factors for them. If we look to the joint C, you're going to find that there are 2 members framing into it. The first one is AC and the second one is DC. This means that we are going to have in the distribution factor at point C, we are going to have 2 distribution factor, right? Which is the first one is distribution factor relating C to A, from C to A, and the other one from C to D. So we're going to have distribution factor for C, D, right? Okay, and we said that the denominator for this distribution factor is going to be the summation of the relative stiffnesses of all members framing into the same joint. We have member AC and we have the member DC, and the relative stiffness of member AC here, this member, or let's call it like CA. Okay, far end is what is fixed, and also CD, the far end is what? Fixed. As we said many times, the joint here, this means that it is as if it is fixed. Okay, so this means that we are going to use I over L to represent the relative stiffness. I here, it is 800 over L, which is 20. So then we are going to put DFCA. Already it is given here. So the first one is going to be 800 over 20, 800 over 20, plus this one, The inertia is 1600, so it is 1600 over 30, which is the distance here. So this is the denominator. However, the numerator is going to be the element that we are talking about. In our case, we're talking about CA, so its relative stiffness is 800 over 20. Then we're going to find this to be 0.429. This means, what is the meaning of 0.429? It means that whenever there is any moment that is going to be developed at this point C, it is 42.9% of it, of this moment, is going to be carried by this member, which is CA, and the remaining, which is 57.1, is going to be carried by this branch. Okay, that's the meaning here. This is 0.429. Then we need to calculate the distribution factor here. We have two options. The first one is to calculate it again, as we have done for CA. So we're going to do it for CD. Or we can simply say that if one of them is 0.429, then the second is going to be 1 minus 0.429, then it is going to be 0.571, okay, which is this value, because as you know, the summation of the distribution factor at any point should equal to 1 unity. So if we have 0.429, then if we sum up with it the CD distribution factor, it should equal to 1. So we are having it to be 0.571, as you can see here, the distribution factor for CD. Okay, or we can calculate it if you want. You can check it. The denominator is going to be the same exactly as here. However, the numerator is going to be 1600 over 30, which is for member CD. CD, it's 1600 over the length. Okay, now we know well what is the distribution factors, or what are the distribution factors at point C. Okay. Now let's go to the point D. Let's remove here everything for point D. If you look here, we are going to have 3 branches. This means that we are going to have 3 different distribution factor. So we are going to have distribution factor for, let's assume it's DC, and then another distribution factor for DB, and another distribution factor for DE. So we have DE here. Okay, so we need to calculate all of them, and remember that the summation of all of them should be equal to 1. So you are free actually to do whatever that you want to do. You can calculate DC and DB and then just subtract them from 1 and give DE, or you can calculate all of them for checking purposes. Okay, now let's go and see how DC and DB and DE is going to be calculated. Remember, well, only one thing that is need to be understood here. When you look to D and looking to the far end here, which is C, it is here, it is fixed, and B, it is fixed. However, for E, it is hinged. This means that the relative stiffness of member DE is going to be exactly 3 over 4 I over L. 3/4 of I over L would be used, or 3/4 of the common inertia or the common relative stiffness is going to be used. Okay, so now let's see how to calculate this in our case. First of all, yes, these are the 3 members, DB, DC, and DE. The first thing to do is to put the denominator for all of them, because they are common in the denominator. So we have 3 members. This is point D. We have 3 members, DC, DB, and DE. So the first one, which is DC, it is going to be 1600. The far end is fixed, or let's start with this member, which is DB. The far end is fixed. The inertia is 800 and the length is 20. So then it will be 800 over 20. This will be repeated for all of them. So the same, as I said, the same denominator is going to be used for the 3. So let's calculate it first. So this is the first term here. The second is going to be DC. Far end is fixed, and we have the inertia to be 1600s. So this means that its relative stiffness is 1600 over 30. So this is the second term. And the third term is going to be 1600 over 30, but the far end is hinged. So it is going to be 3/4 times 1600 over 30, right? Which is the third term here. Okay, so take care of the 3/4 here, which is related to the far end is hinged. The far end is hinged. So when you calculate this for dB, we're going to put here 800 over 20. This is for dB, 800 over 20. So now, if you calculate this, it gives you 0.3. It gives you 0.3. Okay. So always the distribution factors should be less than 1, as you know. Okay. Now let's go to the DC. So we have now DC. It is going to be the same. Denominator is going to be used here. However, the numerator is going to be the only difference. So for DC, it is 1600 over 30, and the far end is fixed. So we are going to use 1600 over 30. If you calculate it, you are going to find it 0.4. Then, based on this, if you know the two distribution factors, then the third one can be calculated easily, which is going to be 1 minus 0.3 minus 0.4. So it gives you 0.3 here. Or you can calculate it. So for a check, as a check for you. So the check for DE, the far end is hinged, then we're going to use 3/4 over 3/4 times 1600 over 30, all of them. We're going to put it here. So this is the numerator in this case. Then we have the distribution, all the distribution factors at point D. Already we calculated for point C and we calculated for point D. What about point E here, which is ED? What is the distribution factor here? It is going to be used. The distribution factor is going to be 1, means that all the moment is going to be here, and we are going to make one time balancing at this point, and then we will leave it after that, as we are going to see in the next slide. Okay. Okay, now let's go to the next point, which is related to the fixed end moments. The fixed end moments. Now, in our case, we have the distribution factors, which are at point C. This is point C. And then this is at point D. We have 3 different distribution factors at point D. Take care. This is point D. We have this distribution factor, DC, which is 0.4. And then DB, which is 0.3. And then we have DE, which is 0.3. Okay, so we have 3 distribution factors. And then at ED, we are going to have only 1, which is the distribution factor at point E. And for point C, as we said, we have 2 distribution factors, 0.429 and 0.571. Okay, now these are the distribution factors that we've got. Now, the second step, if you recall what are the steps for the solution from the previous videos, the second step is the calculation of the fixed end moments. The calculation of fixed end moments. So we are going to use the fixed end moments expressions, which is already given in the back cover of the textbook, which are given in the back cover of the textbook. You can recall them. So actually you are going to find the most common used one is the fixed end moments when that we have a concentrated load at the middle, because we have this case for member CA, right? And then you're going to find that it is very easy to have it. It is going to give you, this is the fixed end moments at the middle. Okay, so it is going to be 100 here. If we are going to talk about AC or CA, they are going to be the same. So the fixed end moments is going to be something like this. And if we have the distributed load to be 40, for example, here, so it is going to be PL over 4, for example, with this distance. Okay, 40 times 20, okay, over 8. So we are going to find this to be 800, which is going to be developed at the ends. This is the fixed end moments, okay, at the ends. Remember that this is counterclockwise, so it is going to be positive. This one is clockwise, so it is going to be negative. So this means that fixed end moment, which is, if we're going to talk about this member, if the member is like this and the force applied is like this, so we have the moments to be developed like this. So one of them is going to be positive, the other one is going to be negative. So the positive one is going to be 100, which is AC, and this is AC here, which is 100, and the other one, CA, it will be with the negative sign and the same magnitude, which is 100 exactly. And then for members BD, let's go to BD and DB. There is no fixed end moments here because we do not have any external loading. So for BD and DB, it is going to be 0 for us. Okay, now let's go to member CD and DE. CD and DE. Actually, they are the same because we have like two spans loaded with the same type of loading, which is distributed loading, right? So this means that we're going to have here this moment, which is going to be positive here, and this moment is going to be positive with the same amount or the same magnitude and sign. So it will be WH squared over 12, for example. Then we're going to have it positive. So this is why we said that fixed end moment CD, which is here, this is CD, and fixed on moments DE, which is going to be here. Okay. Then we are going to fixed end moments, the opposite, which is the DC and ED. So it is going to be here, which is negative here, and another one which is here, which is negative. So it is this one, which is DC, which is going to be negative, and then this, which is ED, which is going to be negative also. And they are going to have the same value, which is 150. So now we are having the fixed end moments for all members. We have the fixed end moments for all members. So now we are going to put it in our table. Okay, so the fixed end moments is going to be for AC and CE, take care, it is positive, and here it is negative, 100 each. For member CD and DC, CD and DC, they are going to have the same magnitude with the different sign. So we have positive 150. Yes, this is one is positive and one is negative. I think there should be something here. I think this one is negative. I think so. CD, this one is positive because it is counterclockwise. This one is clockwise, so it is negative. I think there missed something here. It should be minus here. Okay, similar for DE and ED. DE and ED. It should be positive here and it should be negative here. So take care of this. Okay, I think that the sign is wiped away maybe because of the copy-paste process, but anyway, it is, as I said, based on the sign convention that we have. Okay, there is one thing that is important to highlight. At point D, actually we have like 3 branches, not 2 branches. When we were talking about the continuous beam, we were talking about 2 branches only, so we put like DC and DB and that's it, for example. But here we have 3 branches. So this means that we need to put this branch, which is DB, because there are some carryovers that are going to be given here. We're going to put it in a separate column. Okay, so we need to put it in a separate column, as you can see. Okay, And as we did before, DB and BD, they do not have any fixed end moments, so here we have 0. Okay, we don't have anything for member BD and member DB. It is 0 here and 0 here. Okay, now I think that we are clear with the moment distribution or the distribution factors and the fixed end moments, which are considered to be the most important two steps in our analysis. Now let's go to the balance and carryover procedure that we're going to have. As you can see here, this is the table, and this is, I think that we have done it like many times. We need to remember that we have done it many times before. So anyway, I'm going to highlight what should we do here. First of all, we need to balance 2 points, which is point C and point D. As we said, we are going to make balancing for the free to rotate joints, which are joint C and D. However, joint A, it is fixed, so it is going to only receive carryovers, as you can see. Okay. And for member ED, it is going to be balanced only once, only one time, and that's it. There is no carryover for it. So remember that if we have fixed boundary condition, it receives carryovers. If we use, or if we have hinge or hinged end condition or boundary condition, and already we used the 3/4 of the relative stiffness in our distribution factors, then you are going to balance it only once, and that's it. There is no carryovers, and just you are going to find that here the moment is 0, as we expected. Okay. Okay. So now this is the general procedure for it. Let's go with the the detailed procedures. So first of all, we're going to balance the joints. It is joints here, okay? It means that C and D together. We are going to balance the 2 joints in the same time. As you remember, I have explained this in 2 videos before, which is the practical implementation of the moment distribution. Instead of balancing C and in one step and then go to join D and balance it and then go back to C and so on, we are balancing both together. Okay, now if you're going to look here, we are going to have, I think still we have some problems with the signs here. This is positive, this is negative, this is positive, and this is negative, I guess. Okay, so we are in the right page here, and this is positive here, and this is negative. Okay, now we are going to balance. Okay, we are going to balance points C and D. If you look to point C, we have only 100 minus and 150 positive. This means that the unbalanced moment is going to be plus 50, right? Plus 50. This plus 50 is going to be distributed between the 2 branches here with the negative sign. Whenever that we balance with the opposite sign of the difference. Okay, so we have 150 minus 100. It is going to give us 50 unbalanced moment. Then 50 times 0.429, it gives us 21.4, and we put negative sign here. Similar, 50 times 0.571, it gives us 28.5, and we put negative sign here. Okay, now let's go and balance point D. When we look to the point D, we're going to find that we have minus 150 here and positive 150 here. And we do not have any fixed end moments here, right? DB, because there is no loading the member DB or BD, right? So in this case, the balance here is what? Already done for us. There is no, we do not need to distribute anything. It is balanced. So this is why we didn't put anything here. Okay, now let's draw the line. This line means that the first round of balancing already done, and across this line we are going to make the carryover. So now we have done step 2, and then let's go to step 3, which is the carryover. So in the carryover, we are going to carry over the moment from this point, which is point C, to the far end here, which is point or joint A. So carryover is going to be with the same sign. Remember that very well. Carryover with the same sign. Balancing, it is negative sign. Okay, or opposite sign. So here, 21.4, half of it is going to be 10.7. And here 28.5, half of it is going to be 14.3. Take care of the same sign. Okay, and then we have here, yes, sorry, I forgot to to say that we should balance this joint, which is joint E. So we have minus 150, minus 150. So it should be balanced with, yes, 150 positive, and the distribution factor is going to be 1. Okay, so it is going to be plus 150. And then close it. We will not do anything again for this. Do not look to this point again. Until that, we're going to look at 0. Okay, so no need to do anything for it. Just balance it once, and then carry over whatever that you have balanced the fixed end moments with. Carry over half of it to the other points. So now this is the line of the balance. Then we're going to make carryovers. We already done this, and then the point E, we are going to carry over the moment, half of the moment, to be given to point D. Okay, so which is going to be with the same sign and half of it, 75. Okay, now let's go to the unbalanced moment. Do you have unbalanced moment here at point C? The answer is no. Do you have any unbalanced moment at point D? The answer is yes. We have carryover moment, which is minus 14.3 here. And we have a carryover moment, which is already given from point E. It is plus 75. So when you sum them up, you're going to find that 75 minus 14.3, it is going to give you 60 something. Okay, then it is going to be, the 60 is going to be distributed among DC, DB, and DE based on the distribution factor. So 0.4 times the unbalanced moment, it gives you, okay, and it seems that the unbalanced moment is going to be positive. So all of them, they are going to be negative, as you can see here. Okay. Okay. So based on this, we are going to multiply the unbalanced moment by 0.4, 0.3, and 0.3, then get these values respectively. Okay. Do we have anything to balance here? The answer is no. Then we have balanced point D, no balance at point C, no balance at point E. Then we can draw the line which is ending the round of balancing, and then we are going to make carryover. Fortunately, there is nothing here at point D, so there is no carryover would be carried here, and also at point E. So we should drop it now. From now on, we should not think about it. Then we have only what? Yes, the moments at point D, at this point, which is for DC. Half of it will be here, which is minus 12.2. And for this one, it is 18.2. Then we should make carryover? No, we should not make any carryover for this. Stop it here. Do not think about it. Okay, what about 18.2? Yes, there should be some carryover because we have DB, so there should be some carryover here, which is going to be, yes, exactly, which is half of it, minus 9.1, minus 9.1. Okay, in a similar fashion, this is going to give us a round of balancing moments, so minus 12.2, we're going to distribute it between CD and CA based on the distribution factor. So we'll have 5.2 here, 7 here, and we are not going to have anything here. We will not have anything here. Okay? Okay. And then remember that because this member, which is BD, the end is what? It is fixed. If we go back here, this is fixed. It is like A, so it is only receiving carryovers. So we are not going to carry over back from these points to the other points. We'll not do this. So it is going to be treated as point A. Look, point A. It is only carry over here. We do not carry over back. It's only because it's fixed. Similar here for BD. Actually BD, it is fixed. So we are going to carry over to it. Something, as you can see. Carry over to it. Okay, so that's it. Then we are going to remove and go with the same balancing and carryovers until that we reach to the end where that small amount or negligible amount of moment is going to be remaining. Then we are going to stop it. There is no need for any kind. We are going to stop at balancing case here, and then we are going to sum up all the moments at each point, as you can see it here, and then we can draw the end moment at the end. Let's go to the next slide. So here, this is the final moments. Then we have at AC, it is 92.1 positive. Then it is 92.1 positive, as you can see it here. And then minus 115.5 for CA, minus 115.9 for CE. Take care, this is positive, this is negative. So means that negative, it is clockwise. Here it is positive, means that counterclockwise. Take care of this. Okay, from here, we can obtain, actually what we want is the final end moments. We do not want to calculate the shears, for example. We didn't ask about this, but if you want to calculate the shear, it is easy. You can take the moment at point A, and then take the summation of moment around A to be 0. Then you are going to find only one unknown, which is this shear at point C. Similarly, the shear at point A can be obtained from summation of Fx, summation of Fx equal to 0. You can obtain the shears. You can do this the same for all other members. You can do the same for all other members. Okay, this is actually brings us to the end of this this video. We have covered how to apply the fixed or the moment distribution method on the frames without side sway. I hope you have understood it well, and see you in the next video. Thank you.